Okay, we're going to talk about the scalar dot product of vectors. Okay, scalar dot product. So product means to multiply. So you might guess that this is a way to multiply vectors together and the answer is a scalar. So to try and give some intuition about this, it's a little bit difficult. So we've got two quantities that we want to multiply together. Let's say we've got a 3 and a 4. So this is a vector of magnitude 3. This is a vector of magnitude 4. They're both in the same direction. So if we multiply these two numbers together, we get 12. Okay, and that's what we want to sort of hope to get. But these are vectors. Yeah. So what if their directions were different? We'd want that to affect our answer here if the direction was different. Okay. I need something to rub this out with. Okay, here we go. All right, so what do we get if the directions are different? Okay, so we've got our magnitude 3 vector here and a magnitude 4 vector down here. So to get these vectors, well, what component? So basically what we ask is what component of this vector is going in this direction. So if we had a vector like this is going this much to the right, and it's obviously going up some amount as well. So how much of this 3 vector is going to the right? Well, if we knew the angle in there, we'd be able to say, well, the length of this down here, if we made this a triangle, we've got the hypotenuse, we want the adjacent side. So the length of this one is 3 cos of whatever theta is. Okay, let's give theta pi on 3. Yeah, I think pi on 3. So cos of pi on 3, yeah, that's half, isn't it? Yep, cos of 60 degrees. Okay, so when we multiply these two together, the bit that's going in the same direction as this 4 vector is 3 cos of pi on 3. So 3 cos pi on 3 times 4, which is 3 times 1/2 times 4, which is 6. Okay, so this is basically what our dot product is. So when we look at the definition, we'll now be able to understand it. So our dot product, I won't rub it out quite yet. So we say, if we call the first vector vector A, so this is the 3 vector of magnitude 3, dot magnitude, vector B, we take the magnitudes of both A and B, and then the cosine of the angle between them. Okay. Now this process of multiplying two vectors together, it's not the only process. We can multiply two vectors together and get out an actual vector. We call it the cross product. But when we use a little dot like this, we're talking about a scalar product, and we always just get a number out. Okay, and we get a scalar quantity rather than a vector quantity. Okay. Now we've got that under control. Let's have a think about some of these properties. What if we had a vector this way and a vector this way, and these two vectors were at 90 degrees? So when we measure the angle of a vector, we always measure between the two tails, so the tail against the tail of another vector. So if these were at 90 degrees, this is vector A, this is vector B. What's A dot B? A dot B is going to be the magnitude of A, whatever that happens to be, the magnitude of B, cos of pi on 2. Now we know cos of pi on 2, that's 0. So now we've got something times 0. So A dot B has to be 0. Okay, so when we've got a dot product equal to 0, we know that those vectors must be at 90 degrees. Okay, let's keep going. What have we got? Okay. Oh, what about A dot A? So a vector dot itself. Okay, so let's put this in. We know that they're going to be in the same direction. So we know the angle is going to be 0. We know the magnitude of A times the magnitude of A, cos of 0. Cos of 0 is just 1. So we get the magnitude of A times itself, magnitude of A squared. So A dot A. And this is a really useful quantity as well. Okay. All right, so there's some properties of dot product, just a few of them. What else do we need to know? Okay, let's give an example. I might stop the recording there and try again. There we go. All right, so let's do this in 2D. And so here's my XY plane. And we've got some position vectors. Our first vector is going to be in the ij notation. We'll call it vector A. It's going to be 1 plus root 3i. And our second vector out this way, vector B, that's going to be 2 root 3 plus, what have I done there? That's ridiculous. Getting confused with complex numbers. I've just been recording all those videos, complex numbers. This is I, this is J vector. What am I doing? Crazy. Okay, there we go. Just because I went to 2D, I think. All right. Get it right. All right, here we go. What's this angle? So this angle, I could make a little triangle here and know that's root 3 in the I direction, in the J direction, root 3 across. So I could do inverse tan of that. That whole angle is pi of 3 or 60 degrees. What about this angle in here? This angle, I get inverse tan of 2 on 2 root 3, which is 1 on root 3. So inverse tan of that is pi on 6. So now I can work out the angle in between the two vectors to do the dot product. Angle in between these two vectors is pi on 3 minus pi on 6, or 60 minus 30, which is 30 degrees. So I get pi on 6 in between the two. Okay, so what's the magnitude of this one? Well, the magnitude of A, square root of 1 squared plus root 3 squared, which is 2. Magnitude of B is the square root of 4 root 3 squared, so I already squared the 2, plus 2 squared, which is 4. I don't know why I did it like that. Okay, so we've got 12 plus 4, which is 16, so root 16, which is 4. So the magnitude is 4. So let's find the dot product. We've got both magnitudes, we've got the angle. So let's go A, sorry, that can be my dot. A dot B, that's just a really large dot, equals magnitude of A. I'm just going to put it straight into the formula. 2 times 4, both the magnitudes multiply together, times cos of the angle between them, pi on 6. Cos of pi on 6 is root 3 on 2. So I've got the root on 2 will cancel out with this 2, so I've got 4 root 3. Okay, wonderful. But that's not the only way we can calculate our dot product. We could have, because this is in ij notation up here, this is a really wonderful thing. I can take the I components, multiply them together, take the j components, multiply them together, and then just add up the solution. And that also gives us a dot product. I'm going to do it in red. Hopefully you can see all the way down the bottom here. I'm not 100% sure if you can see this. Let's just do it anyway. 1 times 2 root 3 plus, so that's 1 from here, 2 root 3 from here, plus root 3 times 2, so 2 times root 3. So we've got 2 root 3 plus 2 root 3 is 4 root 3. It's the same answer. All right, that's a much, much easier way to calculate the dot product. Okay, so if you've got this ij notation, it's very easy to calculate the dot product. Okay. All right, so we can use this solution to calculate angles between vectors. Like it's much easier to calculate the angle between the vector using a dot product. Okay, so if I've got A, let's go with equals 2i minus 3j plus k. Let's go to B, that equals negative I minus j plus 4k. Okay, so A dot B, just in case I missed it off the screen before, we'll be able to see it now. A dot B, I just multiply these two together. I got 2 times negative 1, that's just negative 2. Negative 3 times negative 1, that's positive 3. And then 1 times 4 is 4. So I get an answer of 5. I think I've done that right. 7 minus 2 is 5. Yep, cool. So now I know that this also must equal, the dot product equals the magnitude of A times the magnitude of B times cos of the angle between. And I can use this IJ notation to work out the magnitudes easy enough. So it's easy enough to find the angle between those two vectors. Okay, so let's find the magnitude of A. What's that? That's the square root 2 squared plus 3 squared plus 1 squared is root 14, I think. And then B, magnitude of B, 1 squared plus 1 squared plus 4 squared equals 2 plus 16, that's root 18. Or if you takes you fancy, you could write 3 root 2. Oh, 3 root 2. Okay. Alright, so we've got the magnitudes. Let's find the angle. I've dropped my blue. I don't know where my blue pen's gone. Oh well, not to worry. Black pen it is. Okay, so what have we got? We've got 5 equals what have we got? We've got 3 root 2 times, have I done this right? 9, 10, 14, yeah, that seems right. Root 14 times cos of the angle. Alright, let's just tidy it up a little bit. Can we do root 28 times cos of the angle? That seems okay. That equals 5. Yeah, it's not real nice, is it? We could just do, can that simplify down any? I don't know. I don't think so. Doesn't go into 16, doesn't go into 9. Doesn't go into 4. No, I think that's as good as we can do. So we've got cos of the angle equals 5 on 3 root 28. And we could do inverse cos of that and find an answer. And I think that's right. Oh, look at that. I might even have the answer there. So inverse cos of 5 root 28 is approximately, if you had to give it to decimal places, about 71.6 degrees. Okay. Very nice. All right, let's get rid of that and talk quickly about scalar and vector resolutes, resolving vectors. Okay. All right, let's see how we go here. Now, this is going to look a bit familiar. No, still can't find my blue. It's gone. I don't know where I put it. I dropped it. Okay, let's try. All right, let's draw this in red. Okay, so scalar resolute, I'm just going to do this in 2D. It's similar to what we did before. Okay, so if we've got vector A and vector B, and we want to know how much vector A, how much vector A goes in the direction of vector B, and we just want the scalar. Okay, so that's called the scalar resolute. So the scalar resolute. Okay, resolute means resolving this vector in this direction. Okay, so how much of this vector goes in this way. So we basically want this length here. So if you know the angle, you can just do magnitude of A cos of the angle, and you've got the answer. If we want to do it in terms of the dot products, right? So that magnitude of A, because of this, is almost the same as, so magnitude of A times cos of the angle. That's almost the dot product, but we just need B in there, right? So if we wanted to get this in terms of the dot product, right? If the magnitude of B was 1, then we just have the dot product. So we just want the magnitude of B hat here, which is 1. So if we had A dot B hat, right, the unit vector of B, then we've got the scalar resolute. This gives us a number. It just gives us this length here. That's it in the vector. Gives us that number, doesn't tell us anything else about it. The vector resolute parallel to B, vector resolute, all right, parallel to B. Now, I should write vector resolute of A, vector A, yeah, parallel to B. So we're resolving this vector in this direction, but now we want a vector as the answer. So to get this vector here, there's the same vector that I know how big it is because I've already calculated it, yeah, and now I just multiply it by the unit vector B, and that'll give me a vector in that direction. Okay, so if this was 5, for example, this length was 5, right, multiply it by the unit vector B, right, the unit vector B, which is here, it's in the same direction as B, then that'll scale this unit vector up 5, and it'll be the vector I'm after. So the vector resolute is just A dot B hat, right, that gives you a scalar, and you're scaling up vector B. So multiply that number by the vector B hat, and you've got the answer. Okay. If you wanted to get this vector perpendicular, so say vector resolute of A perpendicular to B, right? So this vector up here, right? What I need to do is start here and finish there. So I need to go minus the vector resolute parallel plus A. So I might write it out. Right on it. Vector resolute of A. I'll just do a perpendicular sign to B. Yeah, won't bother writing perpendicular. You know what it means. Right angles. So that's going to be vector A minus A dot B hat times B hat. Okay. Should we try and work one out? We should do an example. Okay, let's do an example. Let's get rid of this and do an example really quick. We can do that. Okay, so I've got my vector A and vector B. We had them before. Vector A was 2i minus 3j plus k. Ooh, there we go. And vector B is negative I minus j plus 4k. Okay, so first thing I want is the scalar resolute. So let's get the scalar resolute, SR, scalar resolute. So I want A dot B hat. Okay, A dot B hat. Now B hat is just B on the magnitude of B, yeah? Whatever B is, I divide by the magnitude. So I could write this out as A dot B over the magnitude of B. That's the same thing, right? So A dot B hat. So A dot B, it's easy to do in this form. Oh, we already worked it out, didn't we? It's 5, yeah? So I get negative 2 plus 3 plus 4, that's 5. Over the magnitude of B, that was 1, 2, plus 16, that was root 18, which is 3 root 2. Cool. So this is a scalar resolute, of A in the direction of B. Okay, so now let's do the vector resolute parallel. I'll use my little parallel lines there. Okay, so that's A dot B hat, which we've already worked out, multiplied by B hat. So let's multiply so we've got 5 through root 2. Let's multiply it by b hat. So b hat is just times 1 on 3 root 2, right? The magnitude times negative I minus j plus 4k. There we go. So this is b hat, or the unit vector of b, yeah, just dividing b by its magnitude. This is the scalar resolute. So what do I get here? I get 5, I get 9 times 2, which is 18, 5/18 negative I minus j plus 4k. That's nice. Okay, now we want, last but not least, I'm going to use this bit over here. Let's go the vector resolute perpendicular of A perpendicular to B. So I want vector A minus all the thing we just found. So that's A dot B hat B hat. Okay, so vector A, that's 2I minus 3j plus 4k, yeah, minus all this, 5/18 of negative I minus j plus 4k. Okay, now we need to put this together somewhat. How on earth are we going to do that? With great difficulty, I imagine. Alright, we're going to have to expand some of this out and add fractions. Okay, so what have we got? We've got, oh, let's just, I'll just do it, I'll just get rid of this. And I'll go minus minus, which means plus. 518i, we need another plus. 5 on 18j. 4 times this is 20 times, but this is going to become minus when I expand that bracket. So 20 over 18. Sorry, 20 over 18. Yep. Okay. Whew. All right, how do we put all these numbers over 18? Well, it's going to be 36 plus 5, that's 41. 41 over 18i. 3 18s are 54, so it's at 59, oh no, 54, and minus 54, plus that is minus 49 on 18j. Oh, this is prone to errors. Okay, 4 times 18, 36, 72. 72 minus 20, is that 52 on 18k? And then that doesn't cancel, that one doesn't cancel, that one does, 26 on 9, I think. But other than that, I think that's all we've got. Let me check, I think I wrote down an answer. 41, oh no, got that way wrong. Well, unless I got it wrong in my book. I wrote down the wrong vector. This should be 1k. Okay, 1k, what does that become? Hopefully it's just that bit that's wrong. So I get 18 minus 20 is minus 2 on 18. Take out the 18 if you want, 1 on 18 if you want to, and you've got it. Perfect.